Welcome to This Explainer. Today, we're diving into a fundamental question in modern artificial intelligence: why increasing a language model's context window doesn't automatically resolve the challenges of long horizon generation. We'll be walking through a bounded theoretical argument that identifies one necessary condition for reliable generation over extended outputs. Let's get right into it. Our roadmap today follows a precise, logical progression. We'll cover 1. Context is not generation. 2. Reading versus deep generation. 3. The retained state bottleneck. 4. The accumulation of local errors. 5. Preserving consequential task structure. And finally, 6. Theoretical limits and implications.
Starting off with part 1, context is not generation.
If you've been following the recent trajectory of AI scaling, you know it rests on 3 main pillars: increasing parameter counts, expanding training data, and rapidly scaling accessible context length. Now, this trajectory has obviously been incredibly successful. Systems that can ingest entire books or huge code repositories are undeniably useful. But a bit of a rhetorical shortcut has emerged. There's a tendency to treat massive input capacity, the ability to process a huge prompt, as if it were exactly the same thing as long horizon reasoning. It's really the difference between having access to a massive library of facts and actually being able to write a globally coherent book yourself. As we'll explore, treating context scale as a complete solution is mathematically flawed. Which brings us to part 2, reading versus deep generation. To understand this flaw, we have to draw a firm distinction between 2 related but entirely different capabilities. First, we have long context reading. In reading, a large amount of relevant structure is externally present, right there in the prompt. The model can simply reattend to it repeatedly, sort of like looking up facts in an encyclopedia. Second, we have long horizon generation. Here, the system must actively preserve its binding commitments, things like hidden constraints, identities, or decisions, across an extended trajectory that it's actively producing itself. So a model might perfectly access earlier material, yet still completely fail to preserve which of those commitments actually remain binding as it generates new text. This naturally brings us to a critical question. Some tasks require hidden constraints or dependencies to remain recoverable across many, many later stages of generation. So, what actually happens when the information required to make a correct continuation outpaces the model's internal capacity to remember it? We'll explore that in part 3, the retained state bottleneck. To answer that question, we first need to define a concept called the effective preserved task state. Simply put, this is the internal recoverable capacity a system maintains to carry forward required hidden constraints or dependencies across multiple stages of generation. Now, this theory studies a stylized family of deep dependency tasks. And based on this explicit task family, if the required hidden task information takes up more capacity than the generator can actually preserve in its recoverable state, well, exact uniform success across the task becomes a mathematical impossibility. The consequence of this bottleneck is pretty severe. When the information needed for a correct continuation exceeds that retained state, the model simply cannot distinguish between different necessary outcomes. Because it lacks the capacity to keep them separate, different hidden cases are forced to literally collide under the exact same internal representation. Ultimately, you get a cascade of failure. The constraints drop out of the recoverable state. The hidden cases become indistinguishable. And because the system literally can't tell which specific continuation is required, it forces errors on tasks that require distinct futures. Once unresolved task information sits outside the recoverable state, it mathematically guarantees a strictly positive error floor. It just can't remain globally consistent. Let's see how this plays out dynamically in part 4, the accumulation of local errors. When we walk through this across an extended trajectory, it generally follows 4 steps. First, a required dependency goes unresolved because of that capacity bottleneck we just talked about. Second, the model makes a local prediction, which is essentially taking a small guess with a minor risk of error. But the crucial point is step 3. These unresolved dependencies often recur repeatedly across a long generation horizon. This isn't just one single explosive failure. Instead, as step 4 points out, those small local error risks accumulate and compound exponentially, which steadily degrades the global correctness of the entire output. This leads to a really important contrast. On one side, we have unconstrained accumulation, where silent drift occurs. A generated output can remain highly fluent locally, the grammar is perfect, the tone sounds right, while secretly drifting into severe global contradiction because unresolved constraints prompt local guessing. On the other side, we have the alternative, contractive correction, where cross-stage inconsistency is actively bounded. The takeaway here is that without an effective way to correct accumulating deviation, fluency can easily outlast structural correctness. Which leads us to part 5, preserving consequential task structure. The source material introduces a concept called the energetic paradigm. Now, we need to be very measured and clear here. This is presented strictly as a high-level systems perspective. It's a conceptual framework concerned with the necessity of preserving consequential structure across time. It does not imply a complete, proprietary, or ready-to-deploy implementation architecture, and it isn't claiming to have completely solved long-horizon reasoning. It simply frames the theoretical goal. The core takeaway of this perspective is straightforward. When future consistency relies on information that is no longer recoverable from the local token continuation, simply throwing a larger context window at the problem is insufficient. Reliable, long-horizon behavior mathematically requires some stronger form of effective state preservation to actually carry task-relevant state forward. Finally, let's wrap up with part 6, theoretical limits and implications. It is crucial that we carefully bound these claims. This is a lower bound theory for an explicit, stylized task family. It does not establish a universal numerical memory requirement for all of natural language, nor does it prove that every single deployed language model must fail at a particular context length. Real-world systems use varied mechanisms, like retrieval, that this specific abstraction doesn't capture. It's simply a bounded theoretical argument identifying one specific necessary condition for reliable generation. However, the public-facing implications remain highly relevant. Processing a massive prompt is a completely different control problem than safely carrying binding commitments forward across a self-generated horizon. Context access is just not equivalent to state preservation. We have to remember that just because a model sounds fluent locally doesn't mean it's structurally correct, because those repeated mild risks compound rapidly over long horizons. Which leaves us with this final, provocative question. If simply expanding our input context windows cannot, by itself, guarantee structural consistency over long generations, how will future systems evolve? It challenges us to look beyond mere input capacity and focus instead on genuine, long-horizon state preservation. Thank you for joining me for this explainer, and I hope it provided a clear, structured view into the information limits of long-horizon generation.